Welcome to the deep dive. Okay, so when you think of Mars, the red planet probably springs straight to mind, right? Desolate, dusty, cold. That classic image.
That's certainly the Mars we see today, yeah. It's the image we've all grown up with.
But what if that's only, like, half the story? Or maybe even less?
Well, that's what's so fascinating. As we dig into the evidence, it becomes really clear that billions of years ago, Mars was a profoundly different place.
It's still kind of mind-bending for me, the idea of Mars as a blue planet, like Earth,
It sounds pretty wild.
with oceans, actual winding rivers.
Yeah.
It feels almost like something out of science fiction.
It does, but the amazing thing is, the evidence, the sort of geological fingerprints of that ancient water, they're still there.
Wow.
So our mission today in this deep dive is to basically go looking for Mars's lost ocean.
Okay.
We want to piece together all these clues, from orbiters, from rovers on the ground, chemical analysis, stuff that's totally changed how we see the planet.
All right, so where do we even begin looking? How can we be so sure it was ever really there? Is the evidence, like, obvious?
Well, some of it kind of is, especially from orbit. You don't even need to land initially.
Okay.
The orbiters circling Mars, they've sent back these incredible images, and they show these vast low-lying areas in the northern hemisphere.
Low-lying meaning, like, basins.
Exactly. And they are bizarrely flat, really uncannily flat, very much like ancient seabeds we find here on Earth.
Huh. Like you could almost imagine water just sitting there.
Precisely. And not just that. Running along the edge of these massive flat plains, you can trace what looks, it really looks for all the world like an ancient shoreline.
No way. Like beachfront property on Mars.
Sort of. You can almost picture beaches stretching out just like along an ocean edge here. It's quite a striking visual from orbit.
That is amazing. So the clues start from way up high.
Yeah, and what's really cool is how those orbital clues kind of set the stage for what we found when we actually got boots on the ground, or, well, wheels on the ground.
With the rovers, you mean? Curiosity, perseverance.
Exactly. When they landed and started sending back images, they confirmed what those orbital pictures hinted at. They found these enormous channels carved across the surface.
Channels. Like canyons or...
More like dried up riverbeds. They look unequivocally like places where massive amounts of water once flowed.
Wow, okay, so evidence of flowing water, not just standing water.
And not just the riverbeds themselves, the rovers have also spotted deltas.
Deltas, right, where rivers meet a bigger body of water.
Exactly, those fan-shaped deposits of sediment. You only get those where a river dumps its load into a sea or a large lake. It's like finding the ancient mouth of a huge river system.
That's pretty concrete evidence.
It is. And what the rovers add, which is maybe even more compelling, is the close-up geology. They've found layered rock, sedimentary rock.
Okay, and why is that so important? Lots of rocks have layers, don't they?
They do, but these specific types of fine layers, they really only form under certain conditions. On Mars, the way these rocks are layered points strongly towards mud and sand, settling very slowly at the bottom of a calm body of water.
So not just a flash flood, but something lasting.
Exactly. Over potentially millions of years. It's not just sand piling up. It's a geological record book of a watery environment that stuck around for a long time.
Okay, so we've got the big picture from orbit, the riverbeds and deltas on the surface, the layered rocks. What else? You mentioned chemistry.
Right, because these rovers, they aren't just driving around taking pictures, they're basically mobile chemistry labs.
Analyzing the soil and rocks.
And this is where it gets really, really convincing, I think. They've analyzed the Martian soil and rocks and found specific types of minerals, things like gypsum and certain types of hematite.
And these minerals are special because...
Because here on Earth, these minerals almost exclusively form in the presence of liquid water. They're like chemical fingerprints. Finding them on Mars is, well, it's incredibly strong evidence that water wasn't just physically present, but it was chemically reacting with the rocks, changing them.
So it wasn't just sitting there, it was part of the environment's chemistry.
Absolutely. Engaged in chemical processes, leaving these mineral clues behind.
Okay, the evidence seems pretty stacked then. For a wet, maybe even blue, ancient Mars.
It's become the consensus view, yes. The debate now isn't so much if Mars had water, but how much for how long.
And a big one.
Yeah.
Where did it all go? If Mars had oceans, rivers, where's all that water now? It's like a planetary magic trick.
It really is the central mystery, isn't it? A kind of cosmic whodunit. And scientists are actively chasing down a few key theories.
Okay, what's theory number one?
One major idea is that a lot of it was just lost to space.
Lost to space. How?
Well, we think Mars, early in its history, had a much thicker atmosphere than it does now. And critically, it also had a global magnetic field, like Earth does.
Right, our magnetic field protects us.
Exactly. It shields us from the solar wind, that constant stream of charged particles blasting out from the sun.
But Mars lost its magnetic field.
It seems so. Probably as its core cooled down faster than Earth's, the internal dynamo that generated the field shut down. We're still working out the exact timing, but once that shield was gone,
The solar wind could hit the atmosphere directly.
bingo! It just started stripping the atmosphere away bit by bit, molecule by molecule over millions and millions of years. And with the atmosphere went the water vapor.
Just blown away into space.
Blown away by the solar wind. Yeah, it's a pretty brutal way for a planet to lose its water.
Definitely.
Okay.
Okay, so that's one possibility. Lost to space. What else?
Another theory, maybe less dramatic but really important, is that a huge amount of that water might actually still be on Mars, just hidden.
Hidden, like underground.
Exactly. It could be frozen just beneath the surface as enormous sheets of permafrost. Think Arctic tundra, but maybe planet-wide underground. Or it could be concentrated in the big ice caps we see at the poles.
So we know there's ice at the poles now. Could that be some of the ancient ocean water?
It's very likely a significant reservoir, yes. So the water isn't entirely gone, just locked away in ice, mostly out of sight beneath the surface or at the poles.
That's kind of a hopeful thought, maybe. For future explorers needing water.
It is, though accessing it is another challenge. But then there's a third theory, which has gained a lot of traction recently, and it's maybe the most, well, interesting one.
Oh, what's that?
The idea is that a huge fraction of Mars's early water didn't go up into space or freeze underground. It went down into the rock.
Into the rock. How does water go into rock?
Through chemical reactions, water reacts with minerals in the planet's crust. Over geological time, this process creates new minerals, hydrated minerals, that actually incorporate water molecules, H2O, into their crystal structure.
So the water becomes part of the rock itself.
Precisely. The ocean was essentially soaked up by the planet's crust, locked away chemically inside the rock, possibly forever.
Wow. An ocean turned to stone.
It's a powerful image, isn't it? The planet itself basically absorbed its own oceans.
That really makes you think differently about the planet. It's not just that the water evaporated or froze, it became part of the planet's very fabric.
Exactly. And it implies the water isn't lost in the sense of being gone from the planet, but it's transformed and trapped in a way that's very difficult to get back out. It's chemically sequestered.
Which has big implications if we ever think about, trying to make Mars habitable again someday. The water isn't just waiting in a freezer.
Right. It's part of the geology now, a fundamentally different state.
So 3 main ideas.
Yeah.
Blown away, frozen underground, or soaked into the rock. Maybe a combination of all 3.
That's most likely, yeah. Probably all these processes played a role to some extent. The big research questions now are about quantifying how much water went where and when exactly these processes dominated.
It completely changes how you see Mars, doesn't it?
Absolutely.
So the next time you look up at the night sky and you see that faint red dot, remember, you're not just looking at a simple desert world.
Not at all.
You're looking at, well, the ghost of an ocean world. It's kind of a reminder that planets can change dramatically, isn't it?
A profound reminder that worlds evolve, and sometimes elements like water end up in the most unexpected places.
Like locked away inside rock. Beauty transformed, I guess.
You could put it that way. A world that might have once been blue and vibrant now carries its ancient ocean deep within its own dry bones.
An ocean turned to stone. That image is definitely going to stick with me. Thanks for this deep dive.
My pleasure. It's an incredible story Mars has to tell.